In this video, we're going to take a look at momentum and impulse. Now, this video is aimed to be sort of a full course on the concepts. So we're going to look at a range of different quantities that we can arrive at using the concepts here. So some of these principles we're going to look at are the common velocity of the two bodies immediately after impact. We're going to have a look at the impulse acting on the bodies during collision. We're going to look at the average force on each body during the collision. We want to take a look at finding maximum contact force, the impulse due to the resistive force, and finally we'll have a look at the velocity of the combined mass after a certain amount of time. So this video is going to be quite detailed, so stick with it and you will understand the principles from beginning to a well advanced level. So momentum can simply be described as some form of mass in motion. And what that means is if we were to derive or look at the formula used to calculate momentum, you will see that it's just simply mass multiplied by velocity. Now, this doesn't tell the entire story because what happens is momentum, it's a vector quantity. And depending on the direction that we're going in, our answer could be either negative or it could be positive. So as you can see, my sign convention that I'm using here, I'm taking what's going to the right to be positive and what's going to the left as negative. So that's the missing information that you won't see in the formula. Now, in terms of impulse, this is simply the measure of the effect of some form of net force acting on an object over some specified duration. So for impulse, you may see variations with this formula, and one version you may see is just simply force multiplied by time. So that's the force acting over specified duration. And what happens here is this will have identical units, or this will be dimensionally aligned to our momentum formula. So if we were to do momentum or mass multiplied by change in velocity, you will see where the unit here coincides with momentum. So both impulse and momentum, they have a lot of similar characteristics. Now let's get into how we will analyze this question that we have here. So we have this body of mass, it's 20 tons, and we're going to convert that into kilo, just multiply by 1,000, and it's moving with a velocity of 10 meters per second to the right. Now that bit of information that tells us to the right, it's there to indicate our sign convention. Now it collides with a body of 5 tons moving at 12 meters per second in the opposite direction. Again, we will take one direction to be positive, which is we'll take to the right as positive and to the left as negative. Now what we're going to evaluate here is what's the common velocity after impact. So that's what we want to find out here. What's the common velocity after impact? And we have two forms of momentum or collisions that we can analyze. One is elastic collision and the other is inelastic collision. And in one case, the bodies separate and can move in different direction or the same direction. And in the other case, the bodies will stick together and move in the same direction. So what we're going to look at here is when they stick together. So with that, we would have the sum of the momentum, so that's m1 for mass 1 will be used to multiply it by the initial velocity of mass 1. And we're going to sum these. So what we have here then is m2, which is our second mass, and multiply that by u2, which is the initial velocity of our second mass. Now all of that should sum to give a total where we indicate where the masses are now together. So we're going to have our M1 plus our M2 now, and because they will have a common velocity, we're just going to sum these and multiply by V, which is a common velocity. So as you can see now at this stage, we just need to do some substitutions and rearrange the formula to get the common velocity. But there is just one thing to really pay attention to, and that's the direction of our velocities. So let's get the numbers crunched. So M1 is going to be 20,000, and that's just converting 20 tons into kilograms, and that will be multiplied by 10. So that's the initial velocity there, plus our M2, 5,000, 5 tons. Now this will be multiplied by negative 12 because this is going in the opposite direction. So that's what I mean when I say that momentum, it's a vector quantity. Now let's sum the masses. So we'll just add up our 20,000 with the 5,000 there. That gives us 25,000. And this will be multiplied by our final velocity of both bodies after collision. So as you can see, we just need to rearrange this to get V over here as the subject, and that will be equal to 20,000 times 10, which is 200,000. And if we do 5,000 times negative 12, that gives us negative 60,000. And we are going to divide all of this then by the 25,000 that we have. And that 25,000, once again, it's representing the combined mass. So what we're left with here is a velocity, final velocity of 5.6 meters per second. So this will represent the final velocity of both masses combined. And the other thing here is it's positive, so that will indicate that we're moving to the right. Now we're going to look at some elements of impulse. So we want to check out what's the impulse on the 20-ton body after the collision. So now let's check out the impulse. And we're just going to look at the 20-ton body. Now that's where our formula here comes in. So I'll use J to represent impulse, and that equals to the change in momentum. So that's the symbol for momentum, that curly looking P. And that formula that we had earlier was mass multiplied by change in velocity there. Or it's the same as force multiplied by the time taken. But because we're not using time as a factor in this context, we're just using the velocities and the mass, then this is the appropriate formula. Now from our question, we know that the initial velocity of this mass was 10 meters per second. And we know that the final velocity was 5.6 meters per second. So all we have to do here is to work out our impulse using that formula. So mass, again, 20 ton, so 20,000, and that will be multiplied by change in velocity, so 5.6 minus 10. This gives us negative 88,000, and that's Newton seconds. So we can see here where impulse is also a vector quantity because our answer here is negative. Now, if we were to work out the impulse on the 5-ton body, it would be exactly the same. The only difference here is you will realize again how significant the directions are. So I'm going to do the impulse on the second body, the 5-ton body, and you will see exactly what I'm talking about here. So this one here that we got, it's negative, so therefore impulse is to the left. So let's now look at the impulse. So let's now look at the impulse on the 5-ton body and see what difference this will be. So we have the initial velocity here of negative 12 meters per second, and we have the final velocity, which was the same as the previous, 5.6 meters per second. Now it's the same formula, so I'll just write this one as J2, which will be equal to M2 and our change in velocity here. So what we have is 5,000 multiplied by 5.6 and minus, now look at this, because our initial velocity was negative, this will have to show as negative still, so that will be minus that negative 12 right there. So what happens is that will change everything to positive. So what we have is now 5,000 multiplied by 5.6 times 5.6 plus 12, which is 17.6. So you have to be very careful with your signs here. So this gives us a positive now 88,000 Newton seconds. And you can see again where the signs matters significantly. So you have to be very, very hyper aware of what's happening with your directions, hence your signs will be impacted. So as you can see in this case, the impulses are equal and opposite direction. So equal magnitudes, but directions are opposite. Now I'm going to add a slight bit more information, and this is just so that we can go deeper and we have a good variety of scope in this question. So let's say we had the collision time. So collision time, which is delta t, is, let's say it's 0.2 seconds, because this will happen quite fast. And we also have what's known as the resistive force after impact. So this is the resistive force, Fr, after impact, and let's say this is 30 kilonewtons. We can now venture into other territories of analysis with this extra information. So we could look at now stuff like the average force on each body during collision. So if we do that, so the average force on each body during collision, we will use this formula, the F equals impulse divided by time. So let's see how this works then. So I'm going to look at the 20-ton body to begin with, and the impulse for the 20-ton body was negative 88,000. And if we just divide that now by the time taken, which was 0.2, then this is going to give us an average force of negative 440 kilonewtons, or 440,000 newtons. Now what's important to analyze here is the shorter the duration of the time is, the bigger the force. So the force, it's directly proportional to the impulse, but it's inversely proportional to time. So if time is reduced, then the impulse, then the force is going to be much greater. Which is why in boxing matches you will always hear them saying to snap the punches, and that's to do with the force and the impulse. That's a relationship really. So as you can imagine, if we were to look at the average force on the other body, which was the 5-ton, where we had the positive 88,000, the only difference is that would be positive and it would be moving to the right. So one's moving to the right, one's moving to the left. Now another quantity we could look at is the impulse due to the resistive force. We're going to take this over a particular period of time, so say over 4 seconds. Now for some reason I've erased the resistive force that I've written earlier. It was 30 kilonewtons, just to put that into context here. So when we do this, then it's just going to be J impulse due to resistive force, so force times change in time. Now the resistive force will act opposite to the direction of motion, so hence in this case the resistive force would be negative, because after impact we would be traveling to the right, so resistive force negative. So we'll have negative 30,000, and remember this was given, I've just erased it for some reason. So that would just be negative 30,000 multiplied by 4, which is over the 4 seconds period that we have here. So this will give us a final impulse of negative 120,000 newtons second. So that's it for this video. There's a lot more quantities that we could analyze, so if you found the video helpful, let me know in the comment. And if you'd like me to go even further with this, also let me know in the comment. And until next time, I will see you in the next video.